messed up my time.
No, I did that.
I know I was supposed to get a part. No one,
Okay, guys, good morning. I have the group lab reports from the Thursday lab. I'll return. Typically, we return to the corresponding author, but I know that any groups gave a corresponding author. There was one, the Jennifer Brown group. The grades ranged from 9 to 7. There was a couple of 9s. I'll just call the first author Shanjani Patel, Devin Patterson, Laura Marshall, Nathan Hangman, Hunter Erb, Juana Yala, Kimberly Gunby. The others will be either passed out this afternoon or possibly on Monday. So we're doing the synthesis this week, SN2. Next week, double E2 elimination. Twice the fun. We'll be using your dibromide that you made several weeks ago that's been in your drawer. Dibromide has 2 leaving groups, 2 bromines. We'll do a double elimination. As a side note, this is also, I'm lobbying for this to be the next James Bond movie titled Double E2 Elimination. Okay? May I actually send you something about James Bond. I know James Bond. Document Kim. Any questions before we get going? I'll send a key out to this page and the substitution page. Any questions about that substitution page with lots of questions? Riley Green? Any questions about the substitution page with the homework problems? Provide reagents, Tamiflu, synthesis of methamphetamine, have to do with the synthesis of meth. Any questions? Okay, quiz on Monday, substitution reactions. All right, we'll plow ahead then. Elimination. Elimination. Okay, we do elimination reactions. We have potentials for isomers, regioisomers, stereoisomers. Most substituted products is a thermodynamic product. We've always known that. We're making alkenes. Alkenes can be assessed at their stability based on the substitution of the alkene. Nothing new there. The most substituted is called the thermodynamic product because it's most stable. In the context of elimination reactions, that product is called the Zaitsev product. This is the Russian chemist. Okay. I think Zaitsev maybe worked with Markovnikov back in the 1800s, 1880s or so. Okay. Zaitsev product. Up here, this here, which one was the Zaitsev product? Did we point that out? E. It's actually both of these, E and Z. The Zaitsev product has stereoisomers. Okay? They're both called Zaitsev. Of the two, though, which is most stable, E or Z? E is always going to be most stable because your big groups, your priority groups, which are bigger, are going to be trans. Okay? Well, here we go. The Zaitsev product is always a major product in the E1 elimination. Did I underline always? Always in E1. Okay? Thus, if this was an E1 mechanism up here, you can eliminate it in a variety of ways. If it was E1, which product would be formed as major product? This one right here, right? This is your E1 product. Most stable. Why do you get the most stable? Not really explained a good bit here. It's because E1 operates under equilibrium conditions. Okay? And we have to go into discussing that. But because it's an equilibrium, really any of them can be formed. But whenever you have an equilibrium, the most stable is going to predominate. Okay? E2 is not equilibrium. Nearly as much. But it's simple, take home. You always get the most stable possible alkene with E1. All right, but not necessarily with an E2 elimination, which can often give the less substituted alkene. By the way, the less substituted alkene in the context of elimination reactions is called the Hoffman product. Which one above is the Hoffman product in the reaction here? They substitute. This is your Hoffman product. The Hoffman product is not the major product with E1. I'm not going to say what is major product with E2, because E2 you have to consider things. E1's easy, most stable. E2 is not always the most stable. That's what this says. All right, let's look at examples of this. We got this carbon with a leaving group, tetrahedral carbon with a leaving group. Water, just water, probably heat here, I probably left that out. But I'm telling you we're doing an E1. Okay? What product are we going to get? Are we going to end up, we got two choices. We have a beta hydrogen here and a beta hydrogen here. We can put double bond between these two carbons by removing this H in the leaving group, or between these two carbons by removing this H in the leaving group. Where are we going to put double bond in? Up or down? More substituted, which would be up, if you see that. That's why I showed the product with the double bond here. If you know it's E1. Now, this may or may not have stereochemistry. In this example, there's no stereochemistry. The alkene is not stereogenic. But if it was, we know we would get E isomer, not Z. Because E would be the better of the two. But in that example, there isn't. So I'm saying if isomers are possible, you would get E. Okay? And you're going to generate that. See, this is a weak base. Not a strong base at all. It's hardly even a base. It doesn't have a lone pair. It's going to take the proton. But we don't call water a base, do we? No. And one of the reasons this is an equilibrium is because you essentially generated acid. I mean, that's HBr in water. And because it's acid, it can actually go backwards because an alkene can react with HBr. And this is actually an equilibrium. And that's one of the reasons, again, why it's always the most stable, and we can talk about that further. Okay, summary. We've already summarized it. What about an E2? It varies. Let's look at E2 examples. Same substrate with the leaving group, and now let's use a strong base. Since it's a strong base, we know it's going to be bimolecular because that base is a bully. It ain't going to stand back and wait for this to ionize or anything. Here I come. This could do SN2. That's a secondary halide. We can also do E2. And later on, we'll talk about how do you decide when it can do both. But let's say it does E2, which is a concerted mechanism, right? Base takes the H, electrons move in, leaving gets kicked off all at the same time, concerted. No carbocation, also no carbanion. Again, we have H here, and we have H here. Two different beta hydrogens. Here I'm showing removal of this beta hydrogen. This would give the more substituted alkene, just like above, but by a concerted mechanism. I didn't show mechanism above. This would be called the thermodynamic product. You always want to get the more substituted alkene. That's always, if you can, that's the key to it, if you can. Okay? And if we use hydroxide here, you're going to get the good alkene. Let's move below and then we'll come back and explain kind of why. Okay? That reaction will give. Let's say subproduct, the good alkene. On the other hand, let's look below. If we do this reaction with this base instead, this base is going to prefer to take this beta hydrogen. Why? What's the difference in the two bases? There's no difference hardly in base strength. A little bit of difference, but that's not it. What's the big difference between these two bases? Sterics. This base has these wings on it. Okay? So I can't get there because every time I try, I keep running into that molecule. Oh, well now I can, no wings, you can get in there. Okay? Question, which hydrogen is more accessible to this bulky base? The answer is this one, because this H sits between two methyls. This H, it's only connected to one carbon. We can really say that this is sort of a, it gets convoluted because we're talking about the substitution over here. I think you see that there's just more substitution. There's more crowding around this hydrogen. It's more difficult for this to take that H. Taking this H gives you the better product, though. Let's see, this guy just can't take it. And what can't take it? How does it? Because the transition state of getting in here is too high in energy. It's like I got to squeeze in there to get it. That's too high of energy for that transition state. So it doesn't happen preferentially. Instead, what happens? How do we know it happens? Because this is the result in the lab. Instead, when you use a bulky base, you tend to get product that came from extraction of the more accessible hydrogen. But if you take the more accessible hydrogen and do your beta concerted elimination, the double bond is going to be here. And guess what? Compared to the other possible product, this is less substituted. We're going to call this the Hoffman product. And it's not the most stable alkene. That's the more stable alkene, right? But this one had the lower transition state leading to it because of less crowding. Take home. Bulky bases tend to give Hoffman products. Hydroxide is not bulky. It's going to give the good product, the more stable Sasef product. That's what's explained here. I'm not going to read it to you. All right, did we get everything? Less crowded beta hydrogen is taken with a bulky base. Called the kinetic product. Because down here it's just formed faster. Not because it's more stable. It's formed faster because it's easier for that base to get to that H there. So it happens faster. Great, kinetics. Okay. That's just one reason why you may not get the Sasef product. Another reason is a bit more involved. And I've labeled this one as number 2. Seems reasonable. Because an E2 elimination has a stereochemical requirement. Not an E1. But an E2 elimination has a stereochemical requirement. This is another reason we may get a Hoffman product. Okay, here's the requirement. In an E2 elimination, the leaving group and the beta hydrogen that's being abstracted must be coplanar. With anti-coplanar, also called anti-periplanar. Most people call it anti-periplanar, but I just call it anti-coplanar because it's simple. I think it's understandable. Coplanar. Two things in the same plane. Very much preferred over syn-coplanar. Anti-coplanar over syn-coplanar. Very much preferred. Now, side note, I'm not saying syn-coplanar can't happen. I'm just saying anti-coplanar is very much preferred. We'll explain syn and anti down here. If the leaving group of the beta hydrogen cannot become anti-periplanar, then beta elimination will be very difficult. As a result, sometimes the less desirable Hoffman product is formed because the leaving group and beta hydrogen leading to that product could become anti-periplanar, while they could not do so to give the more stable state set product. This requirement must also be considered to determine if the elimination product will be E or Z when stereochemistry or stereoisomers are possible. Note, as already said above, an E1 mechanism does not have this requirement. Okay, only the E2. Okay, what do we mean by anti-coplanar? Syn-coplanar. Well, let's go back and use our human projections. Okay? Here's just the simplest two carbons with the beta hydrogen and a leaving group. Okay, drawn like this, yeah? We could have other things here, right? Simplest as possible though. But let's put this in a Newman projection, right? Looking down here. Actually, this projection is looking here, right? Remember Newman? Yeah? Circle, circle, dot, dot. Carbon in the front here. Bromine going straight up. Right? Bromine going straight up. Second carbon over there. Back. H going straight down. Right? You see this is the same thing? Now there's hydrogens here. I just haven't drawn them here. There's an H here and there's an H here. Right? Because of that, if you drew these in, they'd be like this. Alright? I'm not drawing in the hydrogens. But the H and the Br here are anti-coplanar. And you can see that in the Newman. Here's the plane. Alright? The plane. Here's the plane, right here, like a piece of paper. The bromine and the H sit on the plane of the paper. Now, if the bromine was here and the H was like that, no, it would not be. Plane, like that. Question, are they syn or anti to each other? Here's your bond. One's up, one's down, syn or anti? They're anti. They're anti, and they're coplanar. We call that anti-coplanar. There you go. It's easier to see in the Newman. Should we take time to learn how to do Newmans? We did that back in August. All right? Because we knew this was coming. All right. This is actually syn-coplanar. And if you do this in a Newman, you're going to see that actually the H and the Br are eclipsed. You'd have to draw the H up. It'd be right behind the bromine. Okay? But guess what? We're going to put it in Newmans. Why? Because I suggest that Newmans are easier to look at. If you want my recommendation, Newman. We will be doing Newmans. Okay, we also have this idea with our rings. 6-membered rings is what we focused on. Chair conformations. Look at this. Here's a carbon with a leaving group. Next door, beta hydrogen. This hydrogen is anti-coplanar to the bromine. Anti is also often the same as saying trans. Is the H and the B R trans? Remember your chair confirmation stuff? Are these trans? Bromine's up, H is down. They're trans. Okay? Same as anti. Okay? Are they coplanar? Are they coplanar? You say, well, yes they are. Because I read your hand down. But do you see that they're coplanar? Well, it's not as intuitive, but let's have a model here. And we've got a cyclohexane. We've got a leaving group on one carbon, H on the next. Okay. The leaving group is white there, and let's make the leaving group over here next door. I'm going to have to. I've got the enantiomer here. I'm going to have to pull this, put it here. Okay? Bromine up, sort of back. H here straight down. There's another H here. Okay? I'm looking at the axial hydrogen. Right? Not the equatorial. All right? See how they're trans? Okay? Yeah. But they're also planar. So if I take this and just hold it like that, you see how they're like in a line right there? In that ring, but about that carbon, these two, can you see it? They're trans, everybody agree? But they're also in the same plane. Look at the other H here. Okay? Can you see it coming off? First off, it is not anti or trans, it's cis. But also, is it planar? Well, if this is the plane, forget about that. Is this in the plane with the bromine? No, it's pointing this way. Only that one is in the plane. This is the only one that's planar, and it's the only one that's trans or anti. Okay? These two are anticoplanar, not those two. Here's something important though. For any of the beta hydrogens to be anticoplanar, the leaving group must be axial. If you do a ring flip here and put the leaving group equatorial, none of the beta hydrogens are planar. Let's do that. Let's do a ring flip. All right. Now the leaving group is equatorial. Look at the next door hydrogens. Let's look at these two. See them? Is either one of those in the same plane as this bromine that's sticking up? No. What about these two? Let's straighten that bond up. Are any of those two in the same plane? The bromine is straight up. To be in the same plane, the H has to be straight up. No. If the leaving group is equatorial, none of the hydrogens are coplanar. Thus, it is not going to eliminate from this conformation. It must eliminate from this conformation. And this H is the one that's going to be taken because that's the one that's anticoplanar. Why is the anticoplanar important? I don't think it's really showed here too much. It's because when the base, okay, some type of base, that's a good one, takes the H, these electrons then move right in here, and we're going to put the electrons in and make double bond here. They move in here kind of like backside. Right backside, the electrons are coming in sort of like backside and kicking this off. Okay? If you look at some discussion of that, it allows for the electrons to come in and make the pi bond sort of backside. Right? By dihedral angle, remember? This is a 180 dihedral angle, yeah? Anticoplanar is a 180 dihedral angle. All right, here we go. Show the product through each reaction. How about the first one? There you go. Product. First off, substitution. Because often you're going to have to consider, first off, is it substitution or elimination? Let's ask that first. Is it substitution or elimination? Maybe we're starting with a substitution review, and then we'll move to one that's elimination. Substitution or elimination, anybody got it? This is the type of assessment you need to make with any of these reactions. Who thinks it's substitution? And what's your argument? Think it's substitution? Why?
You have a really good leading group to substitute.
You also need a good leaving group to do elimination. Yeah. Good leaving groups are required for both of them. With a good leaving group, you can do both of them. Potentially. Until you recognize something that is a no-no. Anybody recognize anything that tells you which mechanism it is? I heard it's SN2 because what?
We have a really good nucleophile.
What is the nucleophile? Specifically though. Hydroxide. Yeah, it's a good nucleophile. Strong. You're being strong? Okay, I've used the word strong. It basically means the same, but we've been using the word strong. Let's get rid of that, right? Hydroxide. Good nucleophile slash base. No sterics. But what else is going on?
You got a strong base, but you have a sp3 leading group, but that's more for an SN2. There's going to be substitution, but you don't have a weak base.
Well, SN2 would require a strong base.
Right.
I mean, a strong nucleophile. We call it a nucleophile when it attacks carbon. If it attacks H, we call it a base.
Right, but you have a strong base.
Nobody has recognized that the leading group is on a tertiary carbon? And since it's on a tertiary carbon, we do not do SN2? Yep. Why don't you say something? No SN2. Leading group's on tertiary carbon. Okay?
The E2.
What about SN1? Why is it not SN1? Strong, bully. Gonna be bimolecular. Here I come. Watch out. So it ain't SN2 or SN. What is it?
E2.
SE2, yes. SE2. Strong makes it bimolecular. So your choices are cut in half then. It's either SN2 or E2. But you don't do SN2 when the leading group's on tertiary carbon. So there you go. It's E2. Yeah? Okay. So since it's E2, we're doing a concerted beta elimination. Here's a question for you. How many theoretical regioisomers are possible for this reaction? Like above, on that other page, I drew 3 potential products for that one. How many potential products could you draw here, just theoretically? Then we'll determine which are going to actually form or feasible. But theoretically meaning I do it by removing one of the a beta hydrogen and the leaving group and putting in a double bond. How many are possible? And then also tell me if you're including stereoisomers. If you drew all possible products, how many would you draw? All possible E2 products. Anybody? answer is 3. There'll be 2 regioisomers, but one of the regioisomers will have stereochemistry. Answer is 3. Okay, need to know that. Just like previous process, we went through the process on the previous. Okay. I would recommend identify beta hydrogens. Okay? Let's go this way. Here's the first carbon after. There's the carbon in the leave group. That's alpha. Next one here. Is there a hydrogen here? Yes. We draw it stereochemically. H. Let's call it A. So we can remove that H and the Br and put double bond in here. Okay? Are there any other beta hydrogens? What? Yes, on that methyl. There are 3. I'm drawing in 1 though. Let's call it HB. We could put double bond in between this carbon and the methyl carbon, yeah. Okay? Just because it's projected doesn't mean it's not a carbon that's attached and it's a beta carbon. What about this beta carbon? Does it have a hydrogen? No. No hydrogen there. 2 beta hydrogens. This alkene would not be stereogenic. We need to draw it, see. But this alkene would. That alkene would be stereogenic, so there'd be E and Z. That's your total of 3. All right? Well, let's take time to draw them. One of them would be boom, 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 boom. Okay. This is where we removed HB. And we put the double bond in between the carbon and that methyl that was projected. But there's no projection here. This is now an alkene planar. There's no tetrahedral nature here. Leaving group used to be here. HB used to be there. Okay. What if we removed HA? By a concerted elimination. We're going to have double bond there. This carbon's got an ethyl and a methyl. Ethyl and a methyl. This carbon has a methyl and a T-butyl. Methyl and a T-butyl. But guess what? I drew them like that, but we could also have drawn them like this. Same connectivity, but now we have just different projections there. And that's E and Z. Which is which? This is, what is this? E, Z, okay. What's a proper name of this one, like a chemist's name? What's the name of this product here? Context of this reaction. Hoffman product? Yeah? Over here, by the way, Zaitsev is spelled 1,000,001 ways. Some people spell it with an S, some people spell it with a Z. Okay? I think I spell it with a Z. I think I usually spell it like that. Zaitsev. Zaitsev is really regio, but then it has 2 stereoisomers. It's the more substituted one, right? That alkene is tetrasubstituted. This alkene is disubstituted. Okay? There we go. Just like the previous, we had 3 here as well. Question, which one is going to be the major product? If we were doing E1, it would be hopefully easy. If we were doing E1, which would be the product? Most stable, this one here, right? Mm-hmm. We're not doing E1. How do we know we're not doing E1? Because we got a strong base. Bully base, E2, bimolecular. What's going to be the product? We have to make 2 considerations. They were numbered 1 and 2. The first is bulkiness of the base. Is hydroxide a bulky base? No. It's one of the least bulky bases you can have. Which hydrogen is more crowded? Or let's say the other way. Which one's least crowded? Yes, HB is the least crowded. But hydroxide is not going to have any trouble taking HA. Only a bulky base has trouble doing that. And taking HA gives that the better product. So that's going to happen. Hydroxide will take HA. All right? It's not going to take HB. Bulky base would come this way. But we still have a question though. Which isomer are we going to get? Well, what was number 2? Stereochemical requirement. When the mechanism takes place, it needs to be, okay? That is, the mechanism is going to be this. All right, don't do anything yet. These electrons take the H. These electrons move in. Those get kicked off. Double bond gets put in here by an E2 elimination. Inserted E2 elimination. But how does the HA and the bromine have to be when this happens? Anticoplanar. Are they anticoplanar right now? Maybe you see it, maybe you don't. Here's where I say let's put it in a Newman projection because it's much easier to see in the Newman. Let's draw this in a Newman projection and put it in an anticoplanar. I'm going to get rid of these arrows so we can... Let's just do it like this. Here we go. Newman, just like back in September. Boom. Circle, circle, dot, dot. We can stand on either side, doesn't matter. I'm going to stand over here. First carbon. We're looking at the 2 carbons that are going to become the alkene. First carbon. I see something going straight down. What is that? The tert-butyl. Tertiary butyl is called tert-butyl. Okay? What's coming towards you guys? To my left. Methyl. It's also going up a little bit. I'll call that an ME. All right, that's the ME on the end, methyl. What's on this carbon going behind the board to my right? Bromine. There's the tricarbon. All right, let's look back at the second carbon over here. I see something going straight down. Methyl. That methyl is eclipsed with the T-butyl, going straight down. I'm going to draw it a little bit to the right and sort of maybe like this. Second carbon, I see something coming towards you guys. What is it? The ethyl. To the left. Up and to the left. Up and to the left. It's actually, see all this? That's eclipsed. The ethyl. What's on this carbon going behind the board? Actually, it was there and I erased it. I'm drawing hydrogen, right? And that was H. B or what? A. It's eclipsed with the bromine, actually. We'll draw it like this. Okay? Here's the H that gets eliminated. Here's the leaving group. Are they anticoplanar? What are they here? We can describe this. They're right behind each other like this. They're eclipsed. They are coplanar. You can lay a piece of paper across my arm. They're syncoplanar right now. Okay? Or I can hold it like this. Syncoplanar. We want one of them to rotate and go like this. We can rotate this, front or the back. We want the bromine to be over here. Let's rotate this and put the bromine here. All right? Here we go. Built-in Newman, right there. The back is the same. HA. What's on the back here? Ethyl. The back here is methyl. We rotated the front. The bromine is now here. That's going to put the T-butyl, everything's going opposite. The bromine comes here, the T-butyl is going to come up here. And what else is on the front? The methyl? The methyl is going to go, everything's going opposite. We're rotating 180 degrees. The methyl comes here. Now look at the H and the bromine. Now they're anticoplanar, all right? You could draw a straight line here, okay? Piece of paper. There's the plane. The H and the Br are both on that plane. I will do this, sort of circle them like this. If that was real super thin, there's your plane. Now they're anticoplanar. Now we do the mechanism, and the hydroxide takes the H. You can't see the two carbons here, but now these electrons come in between the two carbons and kick this off. Don't worry about that. Here's the important thing is, when that takes place, your groups are fixed. And we see that the two methyls are on the same side. That's going to be your alkene here. Two methyls are on the same side in your product. Where the T-butyl and the ethyl are on the same other side. So which is it? It's this one here. The two methyls are on the same side of the alkene. T-butyl and the ethyl are on the same side, other side. So this gets set because this molecule is sitting there rotating, but if the reaction is going to take place, it's like, okay, the reaction just took place and the groups are there. The outcome is set by the stereochemical requirement. Is this the most stable product on the board? No, this one is the most stable product on the board. This is your E1 product. All right? This is E1. Never noticed that, but, well, I don't think that matters because over here I'm going to write E2. This is your E2 product. We're doing E2, strong base. Okay, there's other ones for you to work there. Same approach. What are my choices? That's where you start with. I would draw them out. This is a 6-member ring, but we looked at how to assess those. And we'll see what type of questions come up. And there's another question or two down there. Okay. You know, when we went through substitution, we mainly focused on SN2. Then we kind of said SN1, you make carbocation. It's really just carbocation chemistry, which we've seen before, alkene. Really the same thing with E1. We'll do an E1 or two. E1 is carbocation chemistry. First step of E1 is leaving group leaving to make cations, just like SN1. But instead of something adding, you do a fast beta elimination. Okay? And there's not as many details with that. Because if there were details for carbocation chemistry, we would have talked about them back when we did carbocations with alkenes. Okay, let's see what we have here. We're going to start doing some miscellaneous things. When either substitution or elimination is possible, which will occur? First, heat favors elimination. And we actually already kind of mentioned this. Because when you do elimination, entropy is in your favor. And we know that if we heat, then we're magnifying the entropy term in the Gibbs free energy equation. So heat favors elimination. All right? So if we do this reaction here with heat, we can eliminate. And that's an outcome. While we're here, I'm showing you, okay, why is it E1? Well, what type of base do we have? Weak. Weak bases can't do E2s. Just like weak nucleophiles can't do SN2. E2SN2 requires strong bases, strong nucleophiles. At the same time, if you have a strong base, strong nucleophile, it's going to be SN, it's going to be bimolecular. Weak is going to be unimolecular. That's why I'm showing an E1 product. And I'm showing, since it's E1, I'm showing the Zaitsev product. Fully balanced. Could this reaction have did an SN1? Yes. What would be the SN1 product? OH? A substitution, replacement, which is kind of a little more intuitive. You're replacing something. But we call it substitution, so I'm not going to call it replacement. But it's the same thing. Substitution. For elimination is remove. Everybody got the simple. Anybody disagree with this product though for an SN1 product? Okay.
Right there, you show SN1 product.
Nice. That's what I would expect. You're looking at the handout? Okay, good. No, 101 goods, yeah. You gotta know what's in the handout. Notice so. Okay. I knew I should be looking at the SN1 product. Okay. What is my product showing there? What's the difference? How did we get to my product? How did the OH end up over here? You envision the leaving group leaving, making carbocation like both SN1 and E1? But how did we get nucleophile over here? Right? Hydride shift. Because we know carbocation, and then water attacks, etc. Now, I said it in one of the lab review sessions, but I don't think I said it in the other. Anytime you can do a carbocation rearrangement for these reactions, we always want to do that. It went from secondary to tertiary. Anytime you can go to a better cation in predicting these reactions, we want to do that. Okay, there we go. See, down here, two molecules become two molecules. There's no favor in entropy. But up here, two become three. Or if you ignore the water, because really the water didn't do anything, although it probably will take the H because HBr exists, H3O+. But if you ignore the water, one became two. Two became two. More entropy up here. And heat favors entropy, so heat's going to favor this top reaction. We already kind of mentioned that before. Number two, another way to help you decide. Involvement of a good nucleophile will favor substitution, where a poor nucleophile will favor elimination. Look at this reaction. If you take this alcohol, react with HBr, you're going to get a substitution product. The nucleophile here being Br minus. If you do this reaction with HF, though, where the nucleophile is going to be F minus, typically you're going to get an elimination product. Which is a better nucleophile? Br minus or F minus? Better nucleophile. Okay? That's because, let's look at the difference here. I've got the same, so it's a little bit different. I'll do it right here so we're about out of time. Let's just consider you got a cation. It's not the same one there. Br minus is a good nucleophile. It's going to add like a nucleophile, attack the carbon. F minus, on the other hand, doesn't like to attack carbon, i.e. be a nucleophile. Instead, which is a better base? It's actually a better base. If you think about it. Instead, it will take the H and the electrons will move in. The better nucleophile will attack the carbocation. The other one, which is probably going to be a better base, is going to act as a base. All right? Okay, we'll meet upstairs in lab. Upstairs today. Just to say 5, right? I said that about 1 million times in the past 45 minutes.